Good afternoon, everyone. My name is Stephanie Zayas, and on behalf of Carahsoft Technology Corporation, I would like to welcome you to our webcast featuring WPI services and Heli-One. Break down, analyze, and optimize costs without reducing capabilities. Before we begin, I would like to go over a few housekeeping items. All of your lines have been muted to reduce background noise, so feel free to use the chat feature on the left side of your screen to submit any questions you may have throughout the presentation. All questions will be addressed towards the end of the presentation, and if we are unable to get to your question, our team will follow up with you offline. To tell you a little bit about Carahsoft, we are a trusted government IT solutions provider, delivering industry-leading technology products, services, and training to federal, state, local, and education customers on behalf of top-tier manufacturers such as SAP, HP Software, Symantec, VMware, and Adobe. Our contact information will be shown at the end of the presentation, so please don't hesitate to call us for any of your needs. At this time, I'd like to introduce our speakers for today, Michael Halber, Manager of Continuous Improvement at Heli-One, and James Woodard, COO at WPI Services. James, the floor is all yours.
Thank you, Stephanie. First, I'd like to thank everyone for joining Carahsoft, WPI, and Heli-One for today's webinar. As Stephanie said, I'm James Woodard, COO of WPI Services. This afternoon, you're going to hear a great customer success story from Michael Halber. But first, I just want to provide a brief introduction to the tool suite. The Opus Suite is a leading tool for systems and cost optimization. Currently in use by more than 150 customers in 30 countries on 5 continents, including the U.S. DoD, Defense Forces of Australia, the United Kingdom Ministry of Defense, Brazil, Denmark, France, Italy, Sweden, Singapore, and Thailand. The Opus Suite enables simulation of how technical systems and their support solutions will perform in different operational scenarios to enable mission effectiveness at the lowest possible cost. The tool provides world-leading capabilities to quickly break down, analyze, and optimize costs. This results in lower total ownership costs without reducing capability or negatively impacting operations for many different industries to include defense, rail, oil and gas, energy, commercial aviation, and mining. The unique capabilities of the Opus Suite make it ideal for optimizing costs and capabilities of a program during the acquisition phase and at various milestones. Another great use is in performing trade studies along with business case analyses, as programs are faced with budgetary constraints and various mission challenges. With today's budgetary challenges, we will leverage the data within your ERP system to enable you to show the impacts on readiness, understand bottlenecks, and optimize your capability for whatever budget profile you might be faced with. There are 3 main parts to the Opus Suite: Opus 10, SimLox, and CATLOC. Opus 10 is a mathematical optimization tool that can define and optimize the link between cost and capability. With an easy-to-use graphical user interface, an analyst can quickly develop models and understand the problem being defined. Customers around the globe have realized savings of 20 to 30% on their measures of effectiveness. In today's budgetary environment, these savings translate to fewer furloughs and higher readiness. And with that brief introduction, I'll now pass it over to Michael in order to describe further how Heli-One has used the tool suite to impact and streamline their operations.
Hello, I'm Michael Halber, Continuous Improvement Manager at Heli-One. With me here at Delta, British Columbia, headquarters of Heli-One, is Nanvei Du, our senior Opus analyst. This presentation that I'm going through now was already presented in November at International Systecon User Conference in London. Heli-One is an MRO division of CHC Helicopters. CHC Helicopters is a company flying helicopters around the world. You, as I see, most of you are from defense, government organizations. You know helicopters flying for this kind of purposes, but small part of helicopters deployed around the world fly for civil purposes as well. Within this part of operations, CHC is very big, biggest or one of 2 biggest operators. We operate aircraft for offshore oil and gas and for search and rescue. Altogether, about 250 aircraft on 5 continents, and we use Sikorsky, Eurocopter, Augusta, Westland, and Bell aircraft. Heli-One, as I said, is an MRO, maintenance, repair, and overhaul division that serves CHC as well as third-party customers. The size of the company, CHC, is about a revenue of $1.5 billion. This presentation will focus on PBH, powered by the hour offering of Heli-One, and how we analyze the cost and benefit of PBH bids that we offer to third-party customers. What is powered by the hour? Most of you probably are know more the PBL concepts, but the power by the hour is kind of smaller PBL. It has been introduced by many years ago by Rolls-Royce engines, and the principles are the customer pays a fixed fee per hour flown of the system, in this case aircraft, helicopter, and Heli-One provides all serviceable line replaceable units whenever they are requested as a result of scheduled and or unscheduled removal in corrective or preventive maintenance. And the core units that are collected in place of serviceable parts provided are taken care by Heli-One, ILS, Integration Logistics Services, that is using external subcontractors or our Heli-One workshops that have capability to do most of the work internally. We have several workshops located in British Columbia, here in Vancouver, Delta, in Stavanger, Norway, in Fort Collins, Colorado, and now also in Rzeszów, Poland. What are the benefits for customers subscribing to this program? First of all, it's a predictable and smooth budget. You fly more, you pay more. You know how much you are going to pay. This is very important for customers to know, because the cost of maintenance are very cyclical, so to say. Now, this also using Heli-One has some advantages on the same service being provided by OEMs, because usually OEM provides this service after market service to its own manufactured systems. Heli-One, as I said before, is providing the system for different types of aircraft, so Sikorsky and Eurocopter, and also for tip-to-tail, means all subsystem, including engines. Usually, the OEM of the mainframe wouldn't provide this kind of service for engine as well, so the customer operator should, in case of AOG, call several OEMs in order to resolve the problem. So Heli-One benefits of this kind of service is also clear. We have long-term and stable revenue. The backlog is for this kind of contracts are for 5, 10, 13 years. So our backlog of work is well established. Also having not only CHC as a captive market, but also third-party customers, makes our pool of assets larger, so also our asset utilization is more efficient. The focus here in this presentation will be more on cost of maintenance than our sparing. And the problem is that providing price per hour is challenging from the point of view of margin. We know what the revenue is. There's a fixed price per hour, but the question is what is the cost per hour? What is our profit? Usually we will be asked what is the cost per hour in order to calculate the margin. But the cost per hour is something that does not exist in the reality because our costs are not per hour, our costs are per event, unscheduled event, repairs, unscheduled removals, reliability problems, or by very large events of overhauls, scheduled maintenance that occur cyclically, according to cyclicality of this kind of maintenance. So revenue is smooth, cost is bumpy. Another problem is that the contract is usually, as I said, very long term. So in order to offer a price, we should assume many assumptions regarding to the cost, like escalation or the operational profile of this customer, flight hours expected, etc., etc. So many problems. What is our approach to the solution? First, we try to model both streams of revenue and cost during the contract duration. Then to calculate life cycle margin using discounted cash flow. So we discount the cash flow of revenues that is relatively smooth, the cash flow of cost that is bumpy, and then we can calculate something that we call the discounted cash flow margin of this specific contract. The alternative way that we went through is to look for metric per hour of the cost. It was very difficult to find something like that, but I will show you that we did, I think, found something that is workable. On top of all of this, we should perform sensitivity analysis in order to face the long-term contract assumptions. As a part of the solution, the slide before, we have deployed the Systecon suite. At the beginning, we started with Opus 10 and SimLogs that serve us for the spare part optimization, because in the solution of a PBH offers, as it is described, we need to keep spares in our pool and also at customer location in order to provide the service. So Opus 10 is this part of the suite that deals with spare part optimization, was deployed, and then we moved to CATLOG, that is lifecycle cost analysis system. By the way, Opus 10 is the main spare part optimization system that, and SimLogs is the simulation system that in our case we use it for refining of the results of Opus 10 from time to time. We built a database called Silo1 that we populated with all data requested by Opus 10 to do its job, and this data comes from different systems and node systems like personal knowledge, etc., etc. Then the models are built in Opus 10. The same data is being used by CATLOC for lifecycle DMC with some additional data elements like cost breakdown structure, ATA grouping costs, scale factors, etc. So the rest of the presentation will be focused mainly on the CATLOC part of the suite. You can see here, this is a screenshot from Opus. In Opus 10, we can model every system, tail number of the aircraft, with all components installed on this specific aircraft. This aircraft is being deployed in different places, different bases in the world. In this respect, our operation is similar to military operation, then let's say to airline operations. They can share parts, spares being flown over with the next scheduled flight. In our case, aircrafts are, helicopters are short flight systems, and they have spares have to be somehow located in the bases or at the regional hubs. So we not only model the system with all parts and quantity installed and mean time between failure and time between overhaul for scheduled maintenance, and the purchase price that is important for optimization of the sparing. But we also can model the support system. So where the aircrafts are located, where the spares are located. Some of them are at the bases, some of them are at the hub. What is the time to get from the hub to the bases? Is the lateral support allowed between the bases or not? All of this is modeled in Opus 10. Usually the model is one model for one database, per fleet, with all aircrafts belonging to this fleet, model one by one, with all parts installed on each one of them. Opus is being used for sparing, and now we want to use the same model for costing, life cycle cost. So in order to do this, we should add some information, some data elements, and also to build cost breakdown structure. And CATLOG is very flexible in this respect. We can build any cost breakdown structure we want. We can base ourselves on templates provided of NATO or Systecon or few more, but we decided to build our own. It's not only the breakdown structure, it's also how the elements are being calculated, or formula, etc. are also built by us. We also included a lot of parameters to serve the analysis, like contract duration and flight hours for the specific contract projected year by year, and we also can do can include time since overhaul time since new formation components to get exact lighting of this of each part, etc., etc. So we have a lot of parameters as well here. Now, once we have the model and the parameters of a contract have been populated for a specific contract, we can run lifecycle cost analysis for this contract. In our case, let's see, this is a screenshot from CATLOC. All data is for illustrative purposes only, so it's not a real one. The costs, I mean. In this case, we have a contract for 13 years. We are using Augusta Westland 139 two-engine aircraft in this example. And this screenshot is for a main gearbox that is the most costly dynamic component on this aircraft. We assume that this is new aircraft flying 1,000 flight hours per year. And we look into the cost that is going to be incurred during the contract by this specific part and this specific aircraft flying this operational profile. We can see the picture. The picture shows that we have every year projected repair cost. And repair costs in the two first years are zeroed almost because we are covered, it's new aircraft, we are covered by warranty recovery, and this is taken into account. And we have two bold events, cost events of overhaul of this main gearbox that happens every 500 hours, so flight hours. In this case, every 5 years, if this aircraft flies 1,000 hours, this event will occur during the contract. And this is being calculated for each part and part. Of course, for some parts we don't have overhaul, we have life limit replacement. For a very small number of parts, we still use PBH contracts with our subcontractors. This type of costs could also be included because, as I said, we built our structure and calculations according to our own modeling. Now, if we look at the picture of the entire contract, all hundreds of parts installed, we can see how bumpy the cost is. There are two huge costs in year number 5 and 10 because it's not only the main gearbox that is being overhauled every 5 years, but the engines that are very high cost maintenance component are also having the same 5,000 flight hours TBO. There are 2 engines, so this is very significant picture. As you see, the warranty are also another items considered. And by the end of the contract, what we have is something called buyout, because there is cost accrued that is not incurred, and by the end we're supposed to refund the customer with the money accrued on wing for different overhaul and life-limited parts, so to say, to bring the cost of these parts to zero time on wing, or let's say to install 0 times in parts that results also in cost for us. We call it buyout. We can also populate here the suggested PBH price, but this picture is not discounted, it's nominal. We don't have any escalation here, we don't have value of time, time value of money being conserved, so this is not enough for analysis, only first step. Now we can apply escalation. In this case, we assume 2.5% escalation of cost per year, cost and revenue as well. And we can use our interest rate, cost of capital, cost of working capital for the company. And then the picture will look differently. As you can see that it is still bumpy, but the costs that are at the end of the project, for example, are reduced according to net present value of each one. On the summary, we can summarize the present value of the revenue and present value of the cost, and calculate the present value margin, that is revenue present value minus cost present value divided by revenue present value. This kind of analysis helps our pricing group. They can do simulations and see what the margin will be with different prices, but not only that, the buy-out part, sometimes also including buy-in for not new aircraft, are usually being negotiated between the provider and the customer, and sometimes this is being spread out or put under different paying timing conditions that could be also entered and simulated here. By product, we are getting a lot of important financial information for this specific contract. We can see it in cash flow. Year by year, we see that 2 years, it's not a surprise, the year number 5 and 10 will face negative cash flow, and it's better to know it now than to be surprised when we arrive to this year and look into the contract and see the contract is not performing. It's built in the contract at the beginning. You see the accumulative cash flow that is positive during the entire contract duration. So this is not so bad as it looks. We can also provide automatically from the system different cost analysis to break down the cost of the contract by different cost elements: overhaul, repair, life limit, parts, replacement, PBH cost, miscellaneous, etc. You can also break this by technical ATA-based section of the aircraft to see how much is on the naming, engine, rotor blades, etc. This classification is also modeled by us based on ATA codes. Now, this was the analysis of the contract itself, looking at total revenue of the contract, total cost of the contract, timing of each one of the events, escalating and discounting as a contract. But as I said at the beginning, we were also looking for another metric that will show us kind of cost per hour that will be comparable to PBH price. So decision makers will be offered very simple piece of information to do their further analysis for decision making. So this kind of metric was found in this called levelized cost. It's being used by the energy industry today. If you look in comparison of cost of electricity, watt hour, you can see that they are comparing nuclear energy with wind energy and solar energy and all different kinds of energy, but by bringing cost of watt hour of each one of them, taking into consideration not only operational expenses, but also investment in facilities and in some cases also cleaning the area after nuclear power plant is being terminated, for example. So from this perspective, our PBH or offer is very similar for some reason to operating nuclear power plant. Even from the life cycle horizon, we are talking about keeping the aircraft 20, 25 years and more. It's like maybe operating energy facility. So what is the levelized DMC? The levelized direct maintenance cost in this example, in this case, we call it NDMC, is an hourly revenue rate needed to recover all maintenance expenses over the economic life cycle of an aircraft, yielding zero net present value. Economic life cycle of an aircraft could be the total life cycle of aircraft that we buy or we lease, or for the specific maintenance contract, PBH contract. This is a kind of break-even point. The customer, we can say that the levelized cost is equivalent to hourly PBH rate that will create zero profit, zero net present value for this economic life cycle. This can be found by try and error using previously described model, or it could be calculated, and we enter this calculation into CATLOC, and it provides us automatically with levelized DMC, and this is a calculation, and this is a result equivalent to this PBH rate that was found manually in order to levelize or to make equal the revenue and discounted revenue and cost. And now calculation of the margin is very simple. We take the PBH rate per hour minus levelized DMC divided by PBH. We have the same margin as doing analysis of entire contract. Now, sensitivity analysis is very important. Some of the sensitivity analysis steps could be very simple. If you want to just to simulate different escalation factors or discount factors, it's relatively simply because it's across the entire project. But in some cases, like using flight hours that are major factor in defining the timing of the event, this should be done by rerunning the entire model, and CATLOC has this functionality built in, sensitivity analysis. And in this case, for example, we show how we run this model with flight hours that are the baseline, but also we can see what happens if the flight hours will be 20% lower or 20% higher for this aircraft. And I don't have time now to go deeper into this. It's not so simple because, as you can imagine, if you fly more, you generate more events that happen earlier. So from the incurred cost and also from the perspective of time value of money, this works as unfavorable factor for the provider. But on the other hand, we have some maintenance, preventive maintenance that has not flight hours limits, but calendar limits. In this case, it is favorable to fly more than to fly less. We did this in the previous slide, sensitivity analysis on flight hours, but as you can see, we usually use more parameters that we perform the sensitivity analysis on, and we put the results into the tornado chart. In this, we are very happy with this approach because it immediately shows which parameter is important from the risk and opportunities perspective. We can see that flight hours in this case plus minus 20% don't make too much difference on the profitability of the contract, but we assume escalation of 2.5% in this of cost escalation. If the cost goes 4% per year instead of 2%, it's the direct margin will go down by 8%. So this is very sensitive, and for this bit is sensitive for escalation, cost escalation factor, and is here defined as leading downside risk. On the other side, we can see that if we can somehow get out of the buyout, so the improvement of the profitability or margin of this bit will be kind of 4%, more than any other attempts to improve it. And in this case, we, of course, end user of this analysis probably will push the sales force to do more on renegotiating the buyout conditions. To summarize where we are now, what we did, what we are doing, and what we plan to do in the future, all aircraft that are flying in our CAC fleet are modeled. We have 10 different fleets, about 250 aircraft that are modeled for sparing and costing. Now the bidding system, I think both, because bid has also sparing part that we didn't talk about it today, but all these bids are going through this process of analysis today. We cannot run this system for bidding about a year for now, more. We cannot report any improvements in margins or win rates, things like that. It's too early. But for sure, we can report that the approval process by executive management is now much faster, easier, and everybody has a better feeling that the decisions are being made on solid fundaments, on numbers, on analysis, and not on gut feeling. We have few plans to improve our model. We will do it during this year, but they are like probably it doesn't say to you much. If you want to ask questions, we'll be open to explain what we are going to improve. Now, the CATLOC application is used not only for bidding of PBH tenders, analyzing the PBH tenders. We are using it also for budgeting and financial planning. This is already implemented. We are doing next year budget. Our financial year starts in May 1st. We have 3 years plan, financial plan, that the costs have been generated for each one of the systems, I mean tail numbers, running catlog. We are thinking about using the system also for total ownership, concept of the total ownership cost of the fleet. This would be very useful for acquisition decision making. We are buying or leasing new aircraft. It is difficult sometimes to decide if to go with Eurocopter for the C225 or with Sikorsky because of S92. For example, so knowing the total ownership for 25 years, for example, this is the next applications that we are thinking about. This summarizes my presentation, and we'll open now. I open for.
Your microphone has been turned on. Your microphone has been turned on.
Also, we have unmuted all the lines for those that are connected just via the telephone. We do have a couple questions that have already come through. How long has Heli-One been using the Opus Suite, and do you see the scope growing beyond the 17 systems shown in the Opus model on slide 6?
Yeah, so we started to use Opus 5 years ago, and we added CATLOC 3 years ago. The 17 systems, tail numbers shown on this slide is only for illustration purposes. To showing more will make this picture not very clear. And in this specific fleet, we have more than 30 aircrafts now. They are all modeled. As I said, we have 10 fleets with 250 aircrafts. All of them are modeled already.
Okay. What is the size of the team performing this effort?
I can understand that you are asking about the team, that the organic team, that there are modelers, and then there are analysts, end users, etc. So our core team is 2-3 analysts, I think more 3 during this 5 years period for Opus, and 2 for CATLOC. Of course, for Opus, for example, we have more seats. With the software, we bought the network license of 10 seats, because not only the modelers, but also sometimes users, managers could enter the models and do their own investigation of data, or do some analysis as well. For CATLOC, we have 2 seats for now. SimLogs, we have 1 seat.
Okay. It seems like a lot of data is needed. How did you, or how long did it take to gather and reconcile the data required for this analysis?
I can understand why this question is being asked, because always the data is being pointed out as a problem, or for going with implementation of taking long time and being a main obstacle. But our experience is it's more how you face the modeling issue. So if you, for example, in our case, we have to model each one of the tail numbers of the fleet because they are different. It's no standard configuration. Different aircraft fly in Brazil, Norway. There are states in Norway have to have the ice features that they don't need to have in Brazil, etc. So depends how many fleets you have and how different each one of the systems is. If you want to take advantage of this difference, or maybe you have a typical configuration. But if you have not very the fleet, we have 10 fleets. These 10 fleets are divided to 15 sub-fleets. Each fleet has an average, as I said, 20 aircrafts. So it's a big operation. But if you have one fleet or one fleet with few fleets with
like an hour to do
standard configuration, or you can copy one system to another, it's simple. So for us, it takes to build or refresh Opus basic model. It takes about 1 month of modeler work.
Great. So Michael and James, I think that is all of our questions for now.
All right, well, just again, I want to thank everyone for attending the presentation today, and feel free to contact either Michael or myself with any questions.
Thank you.
At this time, I would like to thank Michael and James for a great presentation, as well as all of our participants in WPI and Heli-One for being with us today. We hope our webcast has been helpful for you and your organization. If you have any further questions or would like to request more information, please feel free to contact the SAP team here at Carahsoft. Our contact information is now displayed on your screen. Thank you, everybody, and have a wonderful day.